All right, let's get started. Good morning, everybody. Welcome to another sunny, beautiful morning of chemistry with your host, me, Dr. White. Now, a couple things. First of all, I need to talk about test number 3. Actually, thank you. Test average for the class was an astounding 93. Yes, 93, which is phenomenal considering you people are doing a fantastic job, because I think I've told you this, but if I didn't, I'll mention it. When I was offered to teach this summer, at the beginning last spring, I said, all right, I'll do normal lectures the whole week. I was told by the department chairman, you can't. What do you mean you can't? Well, it's an internet course, so you can't do all the lectures. And normally in the summer, the lectures would be roughly about, let's see, 8 lectures, each 50 minutes long, which is about 7.5 hours. Another hour lectures for the lab. So that takes us to about 9 hours. And I finally convinced the department chairman, well, all right, it's internet. Could I do 5.5 hours? Okay, that's enough. And with that limited amount of lecturing, I also have my YouTube videos from 1105. You people rock. Oh, so does the tea, but you much better. So I'm very happy you people are doing well. All right, let's talk about today's game plan. First of all, I'm going to go over some stuff about test number 4 this Thursday. It's July, it's summer, and Thursday's our test. All right, after that, I'll go through the test key for test 3, and then I've changed things a little. First of all, I will, instead of be going through the equilibrium problem set, I'm going to go and finish up acids and bases. Tomorrow I'll do the equilibrium. Wednesday I'll do the acid bases. Then Thursday I'll finish up some stuff that will be on the final, not test number 4. And then I'll also have a lot of time to go through important stuff from equilibrium and acids and bases. So you'll be well prepared for test number 4. Well, now it works. But anyways, you'll be well prepared. So let's go through something important first. Thumbs up, people. Do you all see the Blackboard announcement? Thank you. All right. I posted on yesterday, about 1, that test number 4 will be this Thursday. And in the morning, I will mail you the password for that. On Wednesday, sometime I'll upload it to the assignment area. And you'll have, just like the other test, till Friday morning, 9 a.m., to upload your answers as a single PDF file. All right, test number 4 has 9 pages, 18 problems. Some of the problems are multiple part. On this one, I don't think I have any multiple choice. Test number 4 will cover chapters 14 and 15, dealing with rates of reaction, equilibrium, including Le Chatelier's principle, and acids and bases. Now, the test number 4 points breakdown, there'll be 41 points on rates of reaction, equilibrium, including Le Chatelier's principle, and 64 points on acids and bases. Acids and bases are more important, therefore more points. And if you notice, it adds up to 105, which means I have 5 bonus points. Time out for commercial from Dr. White. Please note that the extra credit project deadline is also Thursday, let's say 5 p.m. And if you haven't done it already, before Thursday when it's due, email me, not put it in the assignment, email me your project. I'll take a look at it and see if it's right or not and tell you what you need to correct. And that way you should be able to get 10 points. Remember, the extra credit project is optional. And then I have the rest, which you've read before. Well, this Thursday I also have our Zoom lecture. And by Sunday, 1 p.m. or earlier, like I did this last weekend, I'll have your points in Blackboard, your test scores. And then, as I already have done, I will email you your individual points so you can see how you did and where you did wrong. All right, that's test number 4 coming up this Thursday. The other thing, which is a little switch, I realized, yeah, I know why I did it, but it's I think a better way is the labs this week. You have 2 labs, both of them I wrote. Plus, if you want, you can go take a look at the Zoom not equilibrium, acid-base titration. I'm going to switch to labs. Ooh, that looks cool. I'm going to switch to labs. Which way did they go? I'm going to switch to labs. So tomorrow you'll do the acids and bases of food lab, and then Thursday you'll do the titration lab. Both of those I wrote. You can look at the Thursday Zoom lab if you want. And just think of it this way, having Zoom helped you take this class. All right, any questions so far? I haven't said it in a while. Remember, in my class, there's no such thing as a dumb question ever. Also, let me remind you, tonight, I will be having my office hours at 6 to 7 on Zoom. If you have any questions, you need any help, always feel free to stop by and get your help or have me answer your questions. Now, question I would have if I were in your shoes, ooh, I won't do that again. But anyways, if I were in your shoes, I would say, what grade am I getting now? Now, most of you have handed in the labs, and the labs I don't grade hard. You'll look at your lab totals. But how do you determine what grade you have? Well, let's take a look. Thumbs up, people. You see the clean whiteboard? Thank you. All right. There's 2 methods. Method A, take the sum of your 2 highest test scores of 3 divided by 2. You'll get a number X. If X is 90 and above, you're getting an A, 80, 89, you're getting a B, 70, 79, C, 60, 69, D, below 60, F. Nobody, I think, got earned those last 2. Take the other method would be take the sum of your 3 test scores, divide by 3, you'll get a number Y. And if that number is 90 to 100, you're getting an A. If it's 80, 89, B, 70, 79, C, and lower. I don't think anybody is in the lower, so you're either getting A, B, or C at this point in this. And the reason why there are two methods, because at this point, don't forget my grading of your 4 hourly exams, the lowest one is drop. So either one of these will tell you what grade you're getting. If you're not sure, always feel either ask me after class when no one's around, or come to my office hours, and I'm more than happy to explain what you're getting in my class. All right, any questions? Going once, twice. In that case, by the way, did you notice Dr. White got a haircut? I went to my new favorite barber, me. I actually did it myself. It came out pretty good. I gave myself a good tip too. Once in a while, Zoom plays game with me. Thumbs up, people. You see Bronson, Laurie Asset? Thank you. You guys are quick, you thumbs up people. Thank you. All right, let's go back. Important thing, a little review never hurts anybody. Acid base. You should know. What is a Bronson, Laurie, acid or base? Or just think of it as what's an acid? That's a proton donor. Any substance that can donate a proton to something else. So if I can give up a proton or say, take my proton, I'm an acid. What's a base? Anything that accepts a proton. And if I accept protons, that makes me a Bronson-Laurie base or just a base. Now, I told you about what happens to acid and water and hydronium ion. We went through, no, I didn't do this one. I went through earlier some names of acid and bases, and I gave you the structures. I'll do that again before the test. Now, acids and bases react in an equilibrium. You learned about equilibrium. Why the book has equilibrium after acids and bases, I don't know. Don't ask me. Luckily, your instructor knows to switch the chapters. Now, HA is the way chemists abbreviate acid. B is the way chemists abbreviate base. And this is called a neutralization reaction. When you react an acid with a base, the proton is transferred, acid, proton transfer. Base, proton acceptor. And when that happens, when this leaves as H+, you get this anion plus this cation. And they have special names. Now, an important concept is what's called conjugate acid and base pair. And those are two species that differ by one proton. So let's look at this reaction. And if I look here, notice this is HA, A here. I have A minus there. The only difference between those two is H+, and these are conjugates. Now, look out, Dr. White is going Technicolor on you. Now, here I have a compound that goes from B to HB+. It's accepted a proton. The only difference is a proton. So this is a conjugate. Now, by definition, this side is called the acid or base. On the right of the equilibrium, this is called the conjugate, and this is called the conjugate. Now, when we go this way, HA is giving up a proton, so it's an acid. Now, let's look at A minus. When we go this way, now back to HA, has it gained or lost H plus? Now, quick pro trip. Students get real all frustrated and confused here. H plus, just follow the hydrogen H. That will keep it simple for you up here and you'll do it right. It's really H plus, but just look at H. Notice here, no H, here actually H plus. So what happens when you go from A minus to HA? It's accepted a proton. Therefore, this is called, on this side, the conjugate base. And now if we look over here, HB going to be, it's gained or lost H plus. Think of just H. H, no H. So therefore, what's something that gives up H plus? It's an acid, because it's on this side, we call that the conjugate acid. And conjugate acids and bases are important. Let me go through this again. HA, acid, HB, base. By the way, there's no convention saying you have to write the acid first and the base second. I could just easily put B first, HA second. Same thing on this side. Now, first thing is identify conjugates on each side of the equilibrium. Are you getting dizzy now? Hopefully not. But anyways, each side of the equilibrium, you look at the two species that only differ by one proton. So you look here, A, it differs by H and a charge, but think of the H as quickest. That's a conjugate. And notice this lost a proton, proton donor, acid. On this side, B is a base. How do we know that? Because it's conjugate, which has the B, no hydrogen, picks up a hydrogen plus a plus charge. It accepted a proton, it's a base, and here's its conjugate. Then you go backward. Here I have A minus. It goes to HA. Does it give up or accept the proton? Think of H. It accepts it. What's a proton acceptor? H acceptor. It's a base. On this side, by definition, are conjugates. So this is a conjugate base. Finally, we look at this and we look at HB plus. And now, if we look, we have HB plus going to be its conjugate. No hydrogen, it lost the hydrogen plus the plus charge. Anything that loses H plus is an acid. On this side, it's a conjugate acid. And again, species remains when the acid loses a proton is called the conjugate base. And conjugate acid is species formed. I'll never ask you definitions. Seaboard, for example. Dr. White's got to get to work. Interesting. Thumbs up, people. See the whiteboard? A blank piece? Nope. Uh-oh. All right. Thank you. Thumbs up, people. All right, let's look at the following. Label the following as acid-base, conjugate acid, conjugate base. 4 points. All right, by definition, everything on the right is the conjugate. So immediately I can put down here conjugates. Now, let's look at the conjugates. What differ by 1 proton? HI, I minus, 1 hydrogen difference. These are conjugates. Oxygen, H2O, oxygen, another hydrogen plus a plus charge. So these are conjugates. Let's look at W. Here I have HI. I've gone to I minus. What have I lost? H plus. What is something that loses a proton? An acid. Now, let's look at water in this case. It goes from H2O to H3O plus. What has it done? Either it's gained or lost a proton, H plus. Follow the hydrogens. 2 to 3, it's gained a proton. What's a proton acceptor? A base. All right, let's go to Y. Why not? Ooh, that was awful. But anyways, Y, where's its conjugate? X. Going this way, what happens? I have 3, I now have 2. What is something that loses a proton or a hydrogen? It's easier for you. It's an acid, and because it's on this side, it's a conjugate acid. And we're left with Z. Z goes from I minus to HI. It's picked up a proton, think of it as a hydrogen. What's something that accepts a proton, or you can think of it as a hydrogen, and that's the base. And that's how you do it. You know something? These are fun. It's your turn. For this equilibrium or reaction, label W, X, Y, and Z, acid, base, conjugate acid, conjugate base. You try it. 4 points each. At this point, if we're in a classroom at COD, I say, when you're done, look up and smile. Oh, I see some people smiling. If you can't smile or don't have your video on, give me a thumbs up when you're done. All right, I think everybody's done. Let's take a look at this. And what you need to do is find out what are the conjugates. And by the way, on the right side, these are always conjugate, so I can immediately fill this in. That's by definition or convention is a proper one. Now, oxygen here, no oxygen there. So these are conjugates. Notice 2 hydrogens, no plus, 3 hydrogens, 1 plus. They differ by H plus. Nitrogen, 4 here, 3 here. They differ by H plus or just hydrogen. So these are your conjugates. Going from here to here, have we picked up a hydrogen, proton, or given one, donated it? You go from 2 to 3. Oh, we picked up one. What is something that accepts a proton? A base. Base, proton acceptor. Now, if we look at X, we go from 4 to 3. Notice it had a plus charge, no plus charge. What's something that gives up a proton, or you just follow the hydrogens? It's a proton donor. That's an acid. And now we'll look at going this way, and let's do Y. Notice here we have 3, and its conjugate has 2, had a plus charge, no plus charge. Therefore, it gave up H plus. What's something that donates H plus? Just follow the hydrogens. And a proton donor is an acid. It's on this side, and we call that the conjugate acid. And finally, ammonia, it's a base, but let's find out is, and on this side, it's the conjugate base. We have NH3 goes to NH4 plus, it's picked up a proton, H plus. Let's count the hydrogens. What's something that accepts a proton? It's a base. But if it's on this side, we call it a conjugate base, and that's how you do it. And I went overtime. All right. Time for a break. Dr. White has to do his stretching exercises. I'll see you back in 5 minutes. Let's make it 9:57. those of you who are still around, we're pretty lucky how our governor is. Luckily, we got a Democrat, not a Republican, because Governor Pritzker has been doing a fantastic job with the virus problem. And if you look at our state, we're not as bad as states like Florida, Texas, Arizona, where the governors never put a face mask rule or other things. So we're pretty lucky, or I guess pretty lucky. Don't forget, wear a face mask when you're out there. It's still out there. It's still dangerous. I don't know if you saw the very sad thing in the news about someone in Arizona, I think it was, had a COVID-19 party, and the guy who gave it was had COVID-19 and gave it to people at the party, and one of them died so far. It's serious. All right, let's go back to something much more pleasant, acids and bases. All right, switches off on the slide, meaning it won't be on the test. But when we talk about acids and bases, but this is something you should learn for your daily life, acids and bases can be strong or weak. Now, I won't put the equilibrium on the board, but a strong acid is one of those that says, here, take my proton. And the equilibrium, when it gives up the proton, is nearly 100%. Now, X in organic chemistry, remember I'm an organic chemist, are the halogens like chlorine, bromine, iodine. Hydrochloric acid is a very strong acid. You never want that on your clothes or skin. Same thing, nitric is strong, sulfuric is extremely strong. Again, switches off. Now, weak acid says, I got a proton. Do you think you might want a little? Maybe, possibly. It only transfers about 5%. Now, one thing I will turn the switch back on, certain weak acids, which strong acids you ingest, you'll be in the hospital, either in an emergency room or you'll be dead. But weak acids that are very weak and dilute, you know about diluting solutions, we use in our daily life. Example would be vinegar contains acetic acid. It's a weak acid. Now, another weak acid that if I were an organic now, if I were teaching it, I'd show you the structure, but citric acid is the acid found in lemons and limes. And the more citric acid, the more tart it is. You know how, have you ever been into lime? Ooh, that's tart. Well, limes are stronger than, lemons are stronger than limes because there's more citric acid. How many of you are familiar with the super, super sour candy that the last 5 or 6 years, candy makers have taught young children, this is good. I hate that stuff, and all they do is they put more citric acid in. Chemists have found a way to make citric acid. You don't have to squeeze lemons or limes. And you can buy, if I have the right money and credentials, I can buy 50,000 pounds of citric acid. It's a white powder at room temperature, and put it in. Those super sour candies, they just put in more citric acid. All right, but something you should know for test number 4. Weak acids have a sour taste to it. Weak acids have a sour taste to it. How many of you are familiar from various cuisines from different countries? They have a sweet and sour dish. In Sweden, you can have sweet and sour meatballs. If you're in Asian cooking, you have sweet and sour pork, the real stuff, not the stuff Americans buy. And you can get that at Chef Ping, and other different cultures have sweet and sour dishes. And the way they make it sour is put in a weak acid, either lemons or limes or citrus, and there are others too. By the way, tomatoes have citric acid in them too. And if you've ever had a canker sore and you have some ketchup and it burns, that's because of the acid, citric acid in the tomato juice. And you should know that weak acids in certain foods have a sour taste to it. Example, I don't think you're going to do shots of vinegar. Yeah. All right, and bases you can have, and the switches off for this, strong bases, which say, I want your proton. They just rip it away from you. Sodium hydroxide, also called, the old name is lye, and potassium hydroxide, the old name is potash. You don't have to know that, but you should know NaOH, KOH is a base. These are strong bases. Weak bases, oh, I think I might want, maybe I'll take your proton, maybe. Don't want the proton. And the most important one, NaHCO3, baking powder. I'm going to skip the monodiene triprotic. It's summer. That won't be on the test. Now, the following won't be on the test, but I just want to get you ready for something. We talk about strong acids. Remember, you learned in equilibrium, last chapter, if you have an equilibrium, you can do an equilibrium constant. But if you notice here, I have water. And this equilibrium, the amount of water compared to the amount of HA, hydronium ion, HCl plus, A minus, will always be tiny. This will be huge. And therefore, this number, if it was KEQ, the equilibrium constant would be meaningless. So chemists came up with an idea for acids and bases, ignore the water. Don't put it here. Because remember, equilibrium constant, which you guys got right on test number, well, no, you didn't take the test yet. You'll get it right, I hope, is concentration of products divided by concentration of reactants. And therefore, when Ka is large, you got a strong acid because it's going to go whoop this way. When it's small, weak acid, switches off. Same thing for base. You ignore the water, you get Kb, the base ionization constant. And when Kb is large, you get more on this side. Therefore, that's a strong base. When it's small, it's a weak base, switches off here. Switches on is probably one of the most important things I can teach you this semester. Water is amazing stuff. It's called amphoteric, which I'll never ask, and it can be both an acid and a base. That's not what I wanted to do. And here, notice one of these will go here, and one will go there. Here, this is an acid. It gives up a proton. I take it back. This is a base because it accepts a proton. This is an acid. And in any water, you have this equilibrium. Now notice, oh, a little tiny arrow and a big arrow. That means the equilibrium is mostly on this side and you just have water. But there's a small amount of this form. And it's very important. Now, because of that, if we had a equilibrium constant, you'd have underneath here water concentration times water concentration, water squared. This is going to be a large number. If it was KEQ, it wouldn't mean anything. So chemists came up with the idea, let's forget about the water and come up with a new constant, which we call the ionization constant of water, abbreviated Kw. It's named after me. Those are my initials. No, this was in effect long before I was even born, but I still like to think of every time I see that, that's named after me. It isn't, but it feels good. And this is one of the most important things I can teach you this semester. And that's the ionization constant Kw is equal to hydronium ion concentration times the hydroxide. And at 25 degrees C, room temperature, this is 1 or 1.0 times 10 to the minus 14. Now, I used to make students memorize this. Guess what? I'll give that to you, important information. Test number 4. I think I put it already. If you look in the lecture folder, I have test number 4, important information. Yep, know this, know how to use it. Let's take a look real quick. Okay, hopefully everybody can see what I'm going to do. All right, let's take a look at this. I'm going to ask once more, a thumbs up, people. You see the 5 points? Nope. I'm glad I asked. Thumbs down, people came out. All right. Now do you see it? Thank you. All right, 5 points. If the hydroxide ion concentration, remember in brackets, that means moles per liter, concentration. OH is called hydroxide ion. I'll never ask that on tests, but I'll use it in the class, is equal to 1.0 times 10 to the minus 3. What is the hydronium ion concentration? H3O. And come on. Just realized my haste. The plus should be inside the bracket. So what are we trying to find? What are we given? What do we know how to do? We know, and this will be given, so we have this. What do we want to solve for? This. So how do we do that? We want to get rid of hydroxide. I'll divide by hydroxide. Whatever I do to one side of the equation, I have to do to the other. This cancels out. That's the ugliest looking 14. I'll rewrite it better here. And I did. Put this in, 1.0 times 10. This should be a minus. Times 10 to the minus 3. I don't need a calculator. I can do this in my head. Dr. Whitelow is a lot of math. And this is your answer. And that's how you do it. Okay, let me have you try one. And important information, I would give you this. There you go. Try it. You'll like it. Remember, when you're done, look up and smile or do the thumbs up. It's a number I won't answer. 2 more rings in my Stop. Thank you. See, my phone even listens to me. Actually, I have it set up 4 rings and it cuts down. By the way, a couple of years ago, my best friend finally convinced me to cut my landline, and I only have my cell phone. And I have in my house, Panasonic makes some amazing Bluetooth phone that hooks up to your cell phone. I've got about 5 of them in my house, all hooked up by Bluetooth through the base unit to my cell phone. All right, let's get to work. What are we being asked to find? What are we given? Hydroxide equals 1.0 times 10 to the minus 6. What are we also given? And that's the Kw, that's me, no, it's the ionization constant of water. That's what the W stands for, is hydronium times hydroxide equal 1.0 times 10 to the minus 14. Therefore, I'm going to start here. What am I trying to solve for? Hydronium, I want to get rid of this. How do I get rid of that? I divide by hydroxide, this side. Whatever I do to one side, I have to do to the other. This cancels out. Remember, anything divided by itself equals 1. Let's move up a little, give me more room. I now have this. I can put that in. Well, I hate this drawing pen because it's got these buttons that I should change that. My big fingers always hit. Now we have this, do the math, and that's your answer. So that's how you do that. And that's how you use the ionization constant of water to do problems like this. You'll find out probably tomorrow why this is important. All right, moving on. You should know this. Now, I don't know if you've ever heard someone say, "Ooh, that's acidic," or "that's basic," or "that's neutral." Now, an acidic solution is a solution in which the hydronium ion, you should know this. This is one where a way of thinking of it, hydronium ion is greater than the hydroxide ion, and this is acidic. Basic solution is where the hydroxide ion concentration is higher or greater than hydronium. It's called basic and sometimes called alkaline. How many of you have heard of alkaline batteries? I wonder what that means. So acidic, hydronium greater than hydroxide concentration. Basic, hydroxide greater than hydronium. I'll give you time to write that down if you haven't. And finally, the last one, a neutral solution. That's when the hydronium ion concentration is equal to the hydroxide ion concentration. And so let's go through it again. Acidic, hydronium ion concentration greater than the hydroxide. Hydronium greater than the hydroxide, acidic. Basic, hydroxide greater than the hydronium, H3O plus. Basic, also called alkaline. And finally, neutral, that's when the hydronium is equal to the hydroxide. Now, if you think about this, I have a solution. Is it acidic, basic, or neutral? Well, now you got to think about what's the hydroxide, what's the hydronium, which is greater or smaller, or are they equal? Oh, I'm getting a headache from all that. That's hard work. Well, it turns out it is. And a chemist, and one of these days I got to find out who came up with it. I've never done that. Maybe this weekend if I have time. Came up with a concept that allowed you to look at a number and find out immediately, is that acidic, neutral, or basic? And that concept is the pH concept. The pH concept is a scale called the pH scale of small numbers that's used to specify, and I'll never ask you what's the pH scale, the molar hydronium concentration in, and it's very important. This is really only for aqueous water solutions, but that's most of what we use in our daily life. You should know how to use this. This will be given to you important information. Of all the things I'll teach you this whole semester, pH is probably the most important. And the pH which is small p, capital H, is minus the log of the hydronium ion concentration. Now, it's time for a special gift from Dr. White. Now, if the hydronium ion concentration is 1.0 times 10 to the minus x, then the pH is x. Example, pH so the pH of that, if this is going to be 1.0, if it's not 1.0, then you got to use your calculator, logarithm, multiply times minus 1. But Dr. White's always going to give on a test or final. It's 1.0 times 10 to the minus x. Therefore, the pH of this is x. If this is this number, then this is the pH. Now, it's important to know pH goes from 0 to 14. Never less than 0, never more than 14. The lower the pH, the more acidic the solution is. The higher the pH, the more basic it is. It's a logarithmic scale, meaning powers of 10. This is something I will not give on the test, but you should know. When the pH is 7, we call that a neutral pH. That's when the hydronium is equal to the hydroxide. When the pH is less than 7, it's acidic. When the pH is greater than 7, it's basic or alkaline. Basic is what you should remember. And pH is a very important thing. You got a swimming pool, which I did when I bought this house. It came with it. It was above ground. Within 2 years, I had it ripped down because I'm not a swimming pool person, especially in Chicago when that summers they're cold out. You got to check the pH of the water. You should know this. Oh, get away. And you'll see me do this some more in the coming days. But remember, I'll do it again, instant replay. pH goes from 0 to 14. In the middle is 7. In the middle, when you're at 7, you're at neutral. Below 7, you're acidic. And above 7, you're basic. And this is pH scale. Now, many things we measure the pH. One of the most important is your blood. If you ever have a blood test, one of the things they'll measure is pH. If your pH of your blood is just a little above 7, too far above 7, they'll kill you. If your pH is too low, it's acidic. Guess what? You're dead. So the pH of your blood is very important. Let's look at some other things, pH. Everybody see the pH scale chart? Thank you. All right, let's look at a few things. This is interesting. Pure water, and you cannot get pure water out of your tap water, but pure water has a pH of 7.0. Now, depending on the season Is it winter, summer, autumn, or spring, fall or spring, the pH of water will change. One problem I had to deal with, I was in Toledo and it was summer and their pH was close to almost 9, high 8, which I found astounding. All right, let's look at a couple things. What's important? Well, they don't have it here. Oh yeah, lemons have a citric acid in there, pH about 2. Now your stomach has, they say gastric, it's really hydrochloric acid, and it's pH 1. Why is the pH of your stomach at 1? It's acidic. It's got an acid in there. One of the miracles of life is you and I both have cells in our body, in our stomach, that make hydrochloric acid, and in the water, the pH is 1, very acidic. Remember, 7, neutral, less than 7, acidic, greater than 7, basic. Now, what they don't have here, let me see if I can find that other chart I had. Everybody see the pH of common substance? Thank you. All right. In your battery, there's an acid, which is sulfuric, acidic. Your stomach acid, Coca-Cola and Pepsi are acidic. Vinegar has acetic acid that's acidic. Notice the blood is around pH 7. And let's look here. Your shampoos are 7 to 10. They're at 10, they'll probably irritate your skin, which they shouldn't. If we look at caustic soda, which is sodium hydroxide, a base, it's pH 14. And different things in our daily life have different acidity or pHs. And if you notice here, they have the pH of your urine, which they measure if you go and give a urine sample, as one of them is slightly, very slightly acidic. Remember, each one of these numbers is a power of 10 difference. Between 6 and 8 is 100-fold difference in acidity or basicity. All right, looks like I'm this all about out of time. Tomorrow, I will go through the equilibrium problem set. Tomorrow, I'll go through the food lab and we'll finish up acids and bases. So Wednesday, I'll go through the acid-base problem set. And then I have some more stuff that will be on the final, not test 4. And Thursday, I'll go through some of the equilibrium and acid base again. So you'll be well prepared for test 4 on Thursday. And with that, I'll look at the clock. I'm going to let you out a whole 15 seconds early. With that, goodbye. Gang gesund. Be healthy. I'll see you tomorrow. Don't forget, office hours tonight, 6 to 7 on your favorite Zoom channel, Dr. White. And you can always catch me on my YouTube channel, which I'm a star. With that, bye. Have a good day.